Welcome back, everyone. This is Dr. Gallenstein, and here we are for the RStudio demo for lecture number 4. So lecture number 4, we're doing multivariate regression. So this is just building off of the last lecture on single-variate regression or simple regression. As normal, we might have some R packages that we need to install. You'll notice a couple of new ones here, so you want to install those if you don't already have them. I already have them, so I'm not going to install them live on the video, but you just type that in and install it. Go ahead and tell R the packages that you need and import your data set. Whoops. Import your data set here. All right, wages, and notice here we're using wages too. Okay, and so now when we are doing a multivariate regression, we might want to produce scatter plots to visualize multiple different relationships that we might want to include in the regression. So we can use ggplot and produce a scatter plot. So here's a scatter plot of wage and education. So we can tell just from looking at the plot that it appears that there's a relationship between wage and education. But there might also be a relationship between wage and experience. Okay, so we'll do scatter plot. It's a little bit less obvious, but maybe there's an upward trend. I'm not sure. But what we might do is just good practice to kind of generate some scatter plots between the dependent variable, the variable of interest, wages, and some of the other variables in the data set to try to get an idea of what variables we think might influence the dependent variable. That way we know what to include as independent variables, because this time we have multiple independent variables. So scatter plots are just a nice way to do that. Okay, so moving on, we're going to use the LM or linear model, the LM command to perform multiple multivariate regression models. So let's just do that. We learned last time how to do it, and actually this is very, very similar. Notationally, it's very similar to the last lecture of a simple regression. So we're going to create a regression here, and we need to save it. We need to give it a name. So I'm just going to call it model 1. I'm going to do three models here. So I'll call model 1. Set that equal to this. So this is what generates the results for that model. So we'll use the command LM, linear model. We type in the dependent variable regressed on, and we'll start off with two independent variables, education and then plus experience. You'll notice that when we use R, we have to include this additional notation like the on symbol and the plus symbol when we're writing out the model. But this is the dependent variable regressed on independent variable 1 plus the independent variable 2. All right, and we have to indicate the data set. So comma data equals wages, and then we can produce the summary of the results using the summary command. So there we go. Here's our first multivariate regression model in R. You'll read the output in the same way as I mentioned before. You have the intercept term, you have the coefficient on the education variable, you have the coefficient on the experience variable. We have the corresponding standard error, t value, and p value for each of the variables. Okay, and so now just a quick note on interpretation. So if I was reading this, I would say, and let's look at education. If I was reading this, I wanted to interpret the coefficients. First, I'd look to see, is it statistically significant? If it is statistically significant, then I trust that this number is indicative of a relationship between, in this case, wages and education. So it is significant, so then I'll interpret this, and I would say wages are 0.6, I'll round 5, 0.65 rounding. Wages are $0.65 higher for each year of education, holding all other variables constant. Okay, so when we have a multivariate regression model, we have to make clear when we do the interpretation that when we interpret specific coefficients, that it is holding all other variables constant. So here again, this would be wages are 65 cents higher for each additional year of schooling, holding all other variables constant. Likewise, for experience, I would interpret this coefficient as wages are 7 cents higher for each additional year of experience, holding all of their variables constant. Okay, so that's how I'd interpret that. Now with multivariate regression, we can include, even more variables. So let's go ahead and add a couple of variables. We'll add the female variable and the non-white variable, and we'll do this as model 2. And here we go. We have our regression results. This should be familiar. Okay, and so I'll just quickly I'll interpret these two variables just for practice. So for the female variable equals 1 if the person is female and 0 otherwise. And so it is statistically significant, so I'll go ahead and interpret it. So what I find here is that wages are $2.16 lower for an employee if they are female as compared to if they are not. Okay, so that's the interpretation here. Okay, and then for this one, I'll go ahead and interpret this variable. This one is not statistically significant, so I would say there's no relationship between wages and non-white. We know that certainly many times in history and today, this might not always be true. But in this case, there is no relationship between wages and being non-white. That is what we would hope. Okay. And then finally, we can run another multivariate regression model. In this case, what we might do is we see the non-white variable is not statistically significant, so maybe we'll just drop it from the model. And so we'll run model 3. Model 3 is just the same model, but without the non-white variable. Okay, so there we go. All right, next, just quickly, I want to look at how to generate and include interaction terms in a multivariate regression model. We might want to do that. So here I have models 4, 5, and 6, just to illustrate different ways that you can include an interaction term into a regression model. So first, actually I might just write a fresh model here. One way that you could do it is you can create an interaction term. You can create a new variable in your data set that is an interaction term between two existing variables. So I'll just show you how to do that. So I want to create a new variable. I'm just going to create a variable, an interaction term between education and the female variable. And I'll call it edufem. And so I'm going to create a new variable. It's called edufem. And I want this variable to go inside of the wages data set. So I'll do wages, $, edufem. And so that's telling R to create a new variable, edufem, and to put that new variable inside of the wages data set. Okay, and I want that new variable to be equals to the education variable from the wages data set times the female variable from the wages data set. So that's how we would do that. We can create that variable. I can even open up my wages data set and see that it is in there, edufem. So there's the data. There's the variable. So if I want to include that in a regression, I could, let's just say I'll do let's do this. So if I have an interaction term between education and female, I want to include the education variable, the female variable, and the interaction term. So whenever I create an interaction term, I want to make sure that I include the two variables that were used to make it as well. So here's another multivariate regression model where I'll have education, experience, female, and then edufem, so the interaction term. So let's just go ahead and run that and see what that looks like. So here's all of our coefficients. Okay, so we see we have our new variable, edufem, although it is not statistically significant. So if I wanted to interpret this, I would just say that there's no interaction between education and female as it relates to the wage variable. Okay, now if I just imagined that it was significant, I can interpret it. I'll just go ahead and interpret this coefficient as if it was significant, just for the sake of illustration and for practice with interpretation. It's very important to know how to interpret coefficients. Interpreting interaction terms can be difficult, but I'll just go ahead and interpret this one, and hopefully that'll help. So for this one, the way that I would interpret this is I would say that that education, or that wages, actually, hold on. Let me interpret education here on its own real quick to put this into some context. That would help. Okay, so wages are 65 cents higher for each additional year of education if the person is male, holding all other variables constant. Now notice, so what I've done is I've created an interaction term between education and female. Once I have that interaction term in there, of course assuming that it is statistically significant, once I have that interaction term in there, the education variable on its own becomes the effect of education on wage for the condition in which that the female variable equals 0. So now I'm going to interpret this for males. Okay, so this would be the relationship between wage and education for males. And if I wanted to know the relationship between wage and education for females, what I would need to do is I would need to add this coefficient and this coefficient together. Okay, but if I wanted to interpret this coefficient on its own, I would say that the value of an additional year of education is 11 cents smaller for females than for males. So that's to say that wages are 11, so the effect of education on wages is 11 cents per year of education smaller for females than it is for males. Okay, that's how I would interpret this if it was significant. Now, because it's not significant, I interpret it as if it's 0, and I would say that there is no relationship between education and being female with respect to wages. And so because it's insignificant, I would go back and I would interpret this as education for anyone, male or female. There's no difference in the impact of education on wages between males and females because it's insignificant. But if it was significant, I would interpret it the other way. Okay. So there we go. That's model 3. That's if I include an interaction term that I've created. But the nice thing about R is that I don't actually have to create the interaction variable. I don't actually have to create edufem. I could just do this. I can write out my regression model, and I can do educ, or education, times female right there in the regression model. If I hit that, what it does is it will include education, female, it'll include both of them on their own, and the interaction term, and that's what this is. And so you can see that these results are identical. That's just another way of writing it, and it's a way of writing it without having to create a whole new variable. Okay. All right, and so I can do that for other things. I can do education and experience interaction. So I do that here. I can do education and married, interacted here. And so that's how we do interaction terms. Okay. All right, now squared terms. Squared terms, what I'll do, I'll just go ahead and create a squared term. So let's say I want to do education squared. So I'll create a new variable inside the wages data set called edu2, and it'll be equal to the educ variable inside of the wages data set squared. Okay, so that's pretty straightforward. And then I would just run a model where I include edu and edu squared. And, oh, whoops, I didn't include that. So there it is, and here's our model, edu and edu squared. Okay. Now let's say I wanted to do some joint hypothesis testing. I wanted to test some hypotheses, so let's show you how to do that. We're going to need the car library here, so I'll go ahead and tell R that I want that library. So I'll hit library car. Okay, and then let's just say, I'll just repeat model 1 that has education and experience. So let's say I wanted to see, is the coefficient on the education variable statistically different from the coefficient on the experience variable? I can look at those variables. I can see that they're numerically different. One is 0.65 and one is 0.07. But I want to make sure that that difference is statistically significant. So I'll do linear hypothesis. That's the command. I'll use linear hypothesis on model 1. And I want to test this hypothesis. I want to test the hypothesis that educ is equal experience. So I'll just run that. And there it is. It even tells you what the hypothesis is. The hypothesis is that educ equals experience. which is the same thing as saying that EDUC minus experience equals 0. There's the null hypothesis, and we're testing that. And here is the p-value for the test. We can see that it is highly significant, which indicates to us that we would reject the null hypothesis and conclude that the coefficients are in fact different from each other. Okay, now we might want to do a joint significance. So if we had a regression model that included the different job sectors, so we have 4 different job sectors: management, manufacturing, sales, and service in this data set. We might want to include dummy variables for 3 of those 4 factors. We can't include a dummy variable for each. We can only include a dummy variable for 3 of them without falling into the dummy variable trap. So what we'll do is we'll create dummy variables for each of those different categories using the command that we've learned before. So let's do that. And then I'll go ahead and run another regression model. I'll use education, experience. I'll include manufacturing, management, and sales. So I'm going to leave out services. So services will be my reference category. And I'll run that regression. And there we go. Education, experience, manufacturing, management, and sales. Okay. Now what we might want to do is we might want to test the hypothesis. We might want to ask the question, does job sector matter at all? And that is a valuable question in this context, because look at our dummy variables related to the sector. Manufacturing is insignificant, management is insignificant, sales is insignificant. All of these are by comparison to service. And so what this is saying is that working in the manufacturing sector is no different from working in the service sector. Working in management is no different than working in the service sector. Working in sales is no different than working in the service sector. So we might want to ask the question, okay, they're all individually insignificant, but are they jointly significant? That means together, do they provide any value in terms of explaining wages? That would be testing for their joint significance. Well, we can use our linear hypothesis command. We'll use it on model 8. And we'll test the hypothesis that manufacturing is equal to 0, and management is equal to 0, and sales is equal to 0. So putting that another way, we are testing the joint significance of all 3. So we'll test that. It's a very nice command because it shows us our null hypothesis. Our null hypothesis is that all 3 of them are jointly equal to 0. So we can look at the results. Here's the p-value. We can see the p-value is 0.68. That's quite large, well above our standard thresholds. And so what that means is that we fail to reject the null, so we can comfortably conclude that all 3 of them are 0. There is no joint significance of them. And in this context, we could then conclude that the sector doesn't matter for wages in this data set. Okay, and finally, I want to show you another neat code that they have in R, where we can actually report a very nicely formatted results table that would help when you go to report the results in your homework or in a research paper or something. I'm going to use a command called Stargazer. If you haven't, so this is one of the packages that we installed earlier, and we told R that we needed the library for Stargazer. We said that earlier. If you didn't install it and do the library command, go ahead and do that now. We're going to use the Stargazer command, and what the Stargazer command does is it will report the results of the models that we tell it to in a very nice format. Okay, and so these are all details for the format. I won't go into all the details at this exact moment, but what we do is we use the Stargazer command. We put in the models that we want it to present for us, and then we'll go ahead and click Run. And you can see here that it produces a very nicely formatted output table where we have the different models. So here's model 1, model 2, model 3. We have the education variable, experience, female, non-white, the interaction term, the constant. So we can compare across models. In this, you'll see here below the coefficient, here's the coefficient. Below the coefficient in parentheses is the standard error. And then it has stars to indicate the significance level. You'll also see that in the note, the stars indicate the significance levels that we are familiar with. So these stars are very helpful for us because they indicate the significance levels that we're familiar with. Here's the constant term. It also produces or reports the number of observations and reports the R squared. Just in terms of the command here, you enter in the number of the models that you want to report. You have to tell it type text. You can give it a title. Here we say the determinants of wages. Say keep stat, and then we'll say n, that's the number of observations, and r squared, that's r squared. So we're just telling it to use the number of observations and the r squared in the table. So it's just a nice presentation. I just want to show you that. Okay, great. Thank you everyone for listening, and I will see you next time.